Hey folks, welcome to lesson 2.4, writing proofs. Before we get started, let's do some review from 1.8. Why do we keep reviewing? To achieve mastery of the material. All right, name the shape and find the surface area and volume of the shape. Why don't you pause it and give it a shot? Come back. All right, this first shape is called a triangular prism. It is a prism because it's got two congruent bases connected by lateral quadrilateral faces. And it's a triangular prism because each of the bases are triangles. Surface area. We memorized the surface area is capital P times lowercase h plus 2 capital B. What do those terms mean? You must know them precisely. P means the perimeter of the base, so the perimeter of this triangle. H means the height of the triangular prism, so that would be this height. Plus 2 capital B means the area of the base. So that would be this right here, area of that triangle. Okay, perimeter of the base. Well, we got 5 is one side, 5 another side, and we've got 6 on the third side. Height of the triangular prism is 3 plus twice the base. The base is a triangle, so the area of the base is going to be 1/2 times the base of the triangle times the height of the triangle. Well, the base of the triangle looks to be 6, and the height of the triangle looks to be 4. Great. 5 plus 5 plus 6 is 16. 16 times 3 is like 8 times 6 or 48. 2 times 1/2 is 1 times 6 times 4, which is 24. All right, so 48 plus 24, 72. What are the units? Square unit, so meters squared. Let's try the volume. Well, the volume of any prism is going to be the area of the base times the height of the prism. The area of the base. Well, I think we already said it's 1/2 base times height of that triangular face. And then we're going to multiply that times the height of the triangular prism, which we said was 3. Okay, so 6 times 4 is 24, divided by 2 is 12. 12 times 3 is the same as like saying 6 times 6, which is equal to 36. What will my units be? Meters cubed. Volume is always in 3-dimensional space. All right. Let's just erase real quick. And we will try the second example. If you haven't done so already, you want to pause it. Go after that second example. Good. Well, this right here, what shape is it? It's called a cylinder. Cylinder. All right, this thing is a cylinder. Next, we want to determine its surface area. Okay, well, 2 pi r gets me the circumference of the circle. And if I multiply that times the height of the cylinder, it sweeps out all the lateral surface area. Then, if I want to get the surface area of the top and the bottom bases, well, that's just going to be 2 pi r squared. Good, and if I want to get the volume of this guy, what am I going to do? I'm going to take the area of one of the bases, which is pi r squared, and multiply it times the height, and that'll sweep out all the volume. You just memorize these formulas, where r is the radius of the circle, h is the height of the cylinder. That's it. All right, so we got 2 pi. Well, the radius seems to be 6 and the height 10. Plus 2 times pi times 6 was 6 squared. Okay, 6 squared. What do we got? 60 plus times 2 is 120 pi. Plus, we got 36 times 2 is 72 pi. So what are we looking at here? We're looking at 192 pi. And what are the units? Surface area. Area is always 2-dimensional, so centimeters squared. All right, how about the volume? Well, we got pi times 6 squared times 10. 36 times 10 is 360 pi. And what will the units be here for volume? Centimeters cubed, because volume is always three-dimensional. All right, onward to the lesson. Chapter 2, writing proofs. Here's an anticipatory question for you. What is one statement that you have heard that you have accepted as true without requiring any proof? Because the statement seems self-evident to you. So think about this quietly for a minute, then write down your answer. Go ahead and pause it here. All right. What'd you come up with? I'm curious. Did you come up with God exists? That was Thomas Aquinas's first principle. That was his self-evident truth, amongst others. Maybe you came up with a hot dog is a sandwich. Maybe you think that's a self-evident truth. I don't know. In mathematics, a postulate or an axiom is a statement that is accepted as true without proof. Basic ideas about points, lines, and planes can be stated as postulates. So, in a nutshell, postulates are axioms, self-evident truths. We all just accept them as being true without any proof. In philosophy, these are called self-evident truths or first principles, like God exists. All right, here are some postulates or self-evident statements about points, lines, and planes. Let's look at them together. First one says, through any 2 points, there's exactly 1 line. You agree? If there are any points, there's a unique line? Yes, you know that. Through any 3 non-collinear points, meaning not on the same line, there's exactly 1 plane. Do we agree upon that? Yeah, you know this. If there's a point in space here, another point in space down here, and a third point in space, say over here, you can see where that plane is. It's right there. All right, a line contains at least 2 points. Yes, a line contains at least 2 points. In fact, it contains many more points than that. How many? An infinite number of points. It has an infinite number of points. A plane contains at least 3 non-collinear points, not on the same line. Yeah, of course, a plane contains at least 3 points that are not on the same line. That's how you identify a plane. You need 1, 2, and a third point. And these 3 points shape out a plane. Well, how many points are actually on a plane? An infinite number of points, right? If 2 points lie in a plane, then the entire line containing those points lies in that plane. All right, we agree upon that. Yeah. If a line, here's a plane, and here's a line sitting on the plane, then all the points in that line also sit on the plane. How about if 2 lines intersect, and their intersection is exactly 1 point? What do you think? Yeah, most definitely. Look, here's 2 lines intersecting, they intersect at a single point. And then finally, if 2 planes intersect, then their intersection is a line. Well, here, you can see that down here. Looks good. There are 2 planes coming together in a single line. Great. So these statements right here are called postulates, meaning they're self-evident. We don't have to justify them. We just have to agree that they're truthful first principles. In fact, this statement right here, through any 2 points, there's exactly 1 line, was Euclid's first postulate, his first axiom. Euclid being the father of geometry, who wrote the influential book Elements that was for 2,000 years considered the preeminent math textbook. All right. Explain how the photo illustrates that each statement is true. Then state the postulate that can be used to show each statement is true. Lines N and lines P intersect at point D. Well, you can see that that's true. Can you express it in language that a layperson can understand? Sure. We could say something like 2 edges of the roof extended indefinitely. So here's the edges of the roof. They're extended indefinitely in these lines. Intersect at 1 point located at the corner of the roof. You can say that's a corner roof. Which postulate that we just looked at before. We looked at, right, 7 of them. Which postulate makes this statement true? It's postulate 2.6. If two lines intersect, then their intersection is exactly 1 point. All right. Points A, B, and D form a plane. What do you think? Point A, point B, and point D form a unique plane? Yes? Yeah, you would agree with that. When you put it in language the average person can understand. Sure. 3 points are on the front face of the building. They're on the front face of the building and are non-collinear, meaning not on the same line. Yeah. Which postulate from our list of 7 will justify this statement? Points A, B, and D form a plane. It was postulate 2.2. Through any 3 non-collinear points, there's exactly 1 plane. All right, folks, time for guided practice. Points A, B, and C are points that make up line J. See if you can do this and come on back, all right? All right, points A, B, and C are points on the same line. Yeah, we definitely agree with this statement right here. Line J, that is. How would you describe that to an average person on the street? You would say, these 3 points lie on one edge of the building, extended indefinitely, making it a line as opposed to a segment. All right, which postulate you're going to reference? Postulate 2.3, a line contains at least 2 points. In this case, containing 3 that are noted and an infinite more. Okay, next. Try this one on your own. Come on back. The plane that contains A, D, and E, this plane, folks, intersects the plane that contains F, G, and E. That's this plane, folks. In line K. Yeah, we can clearly see this is true right here. How would you describe that to a layperson? 2 faces of the building, extended indefinitely, intersect along an edge of the building, extended indefinitely. Postulate 2.7. If 2 planes intersect, then their intersection is a line. That's clearly what's being demonstrated here. All right. Determine whether each statement is always, sometimes, or never true. Explain your reasoning. If 2 coplanar lines intersect, then the point of intersection lies in the same plane as the 2 lines. Coplanar means on the same plane. So we have 2 lines on the same plane. This is 2 lines on the same plane, namely your computer screen. 2 lines intersect that are coplanar, then the point of intersection also lies in the same plane as the 2 lines. Yeah, that's also on your computer screen. No, this is true, for sure. Is it always true? Sometimes true, never true. Always true. And which of the postulates help us to establish that? If 2 points lie in a plane, then the entire line containing those points lies in that plane. All right, you have to apply it more than once, but that's the fundamental idea here. 4 points are non-collinear. 4 points are non-collinear. Well, certainly here's 4 points. Yeah, I'll draw them 4 points that are non-collinear, right? They're on a plane, they're non-collinear. Well, why couldn't I have 4 points in a row like this? Those are definitely collinear. All right, so this can be true, but not always. It's sometimes true. And what can we use to justify our thinking? It would be postulate 2.3. A line contains at least 2 points, right? So this line contains at least 2 points, but it actually contains a bunch more. This line right here contains, at least 2 points, but these guys are not on the line. Next, pause it. Come back, see how you do. 2 intersecting lines determine a plane. Do we believe this? Here's 2 intersecting lines. Do you know which plane they're on? Yeah, your computer screen. So this is definitely true, always. What justifies it? Which postulate? Through any 3 non-collinear points, there is exactly 1 plane. All right, so maybe we're talking about this point. Okay, maybe we're talking about this point. Wow. Maybe we're talking about this point. Maybe we're talking about this point and this point. That'll work. There's an infinite number of points. They're all on the plane. Try this on your own. Come back. Three lines intersect in 2 points. Is that always, sometimes, or never true? Well, it depends what diagram you have in your head. What they're getting at is something like this. All three lines intersecting at a point. Okay. Three lines intersect in 2 points. That cannot happen. Not all three of them intersecting each other, right? We're not talking about this. We're not talking about something like this. Yeah, we're not talking about that. That's not on the table. That's not what we're discussing. We're discussing where all three lines intersect together at the same point. All right, so three lines intersect in 2 points. Always, sometimes, or never? No, never. Postulate 2.6. If two lines intersect, then their intersection is exactly a point. Same thing goes for 3. All right, to prove a conjecture, you use deductive reasoning to move from a hypothesis to a conclusion of a conjecture you're trying to prove. This is done by writing a proof, which is a logical argument in which each statement you make is supported by a statement that is accepted as true. We're doing proofs, we're doing deductive reasoning. A flow proof uses statements written in boxes and arrows to show the logical progression of an argument. The reason justifying each statement is written below the box. This type of proof allows you to see how each statement is deduced from other statements. This would be the structure of a flow proof. Write the given statement in a box and the word given underneath. Then create a deductive argument by forming a logical chain of statements linking the given to what you're trying to prove. Write these statements in linked boxes and justify each statement with a reason beneath the statement. And then state what you have proved. That's a flow proof for you. All right. Flow proofs come in many languages. One would be an algebraic proof. An algebraic proof is a proof that is made up of a series of algebraic statements. Properties of equality provide justification for many statements in algebraic proofs. So let's look at those. You'll be using these truths when you're doing algebraic proofs. So let's just look at them. They're all pretty evident to you at this point with all your skills in algebra. If I have A equals B, then I can certainly add C to both sides. That's called the addition property. Or I could subtract C from both sides, subtraction property. I can multiply by C on both sides, multiplication, divide by C, division, right? Pretty straightforward. Reflexive property, what's that? That's where something equals itself. Symmetric property, A equals B, then B equals A. Transitive property, if A equals B and B equals C, then A equals C. All right. Yeah. Substitution property, this comes up all the time. If A equals B, then A can be replaced with B. And then finally, distributive property, A times B plus C is the same as A times B plus A times C. All right, do you need to memorize these? You already kind of know all these ideas. They're already there in your algebra skill. Just associate a name with them. That's all. All right, for help with your homework. Prove that if y plus 2 over 3 equals 3, then y equals 7. Write an algebraic flow proof. All right. So what am I trying? What's my given? Is that y plus 2 equals over 3 equals 3. What am I trying to prove? That y equals 7. Let's use a flow proof. Algebraic flow proof. First thing you always write a flow proof is the given. Y plus 2 over 3 equals 3, and you write underneath it's the given. Okay, what would be your first move? If I told you that this proof is basically just doing algebra to solve for y, that's basically what it is. Could you do it? What would be your first move? Multiply both sides by 3, right? And what property is that? That's the multiplication property. All right. Now, if I take 3 and I multiply it times 3, what do I get? 9. 3 times 3 is 9. They're equivalent statements. So in order to simplify this, I'm going to use what's called the substitution property, where I say 3 times 3 is 9, 3 divided by 3 is 1, so I just left with y equals 2, y plus 2. Next step, what are you going to do to both sides if I said solve for y? Yeah, you know it. You're going to subtract 2 from each side. That's the subtraction property. And then finally, you're going to combine like terms. This will equal 7. This will equal 0. That's called the substitution property. Whenever you replace something like 9 minus 2 with 7, which is evident, that's substitution. All right, next. I want you to try this guided practice. Try pausing it and see if you can do it. If not, let's work through it together. Prove that if negative 5 times x plus 4 equals 70, then x equals negative 18. All right, what's our given? Negative 5 times x plus 4 equals 70. What are we trying to prove? X equals negative 18. We're going to do an algebraic flow proof. What do you always write first? The given. What's the given? Negative 5 times x plus 4 equals 70. Next step, what would you do? Like instinctively, if you're doing algebra on this guy right here, what are you going to do? You're going to distribute, aren't you? Good. So let's distribute. Negative 5 times x plus negative 5 times 4 equals 70. All right. Now maybe we want to do a little substitution. What do you think? Negative 5 times 4 is what? Negative 20. Those are equivalent statements. Great. And we call that substitution property. Negative 5 times x is negative 5x. Negative 5 times 4 is negative 20. Next, what would you do next if you were solving this algebraically? What would you do? You'd add 20 to both sides. Great. What do you think that property is going to be called? Addition property. And when you add the 70 and the 20, or add the negative 20 and the 20, you get the equivalent statement. So that's just substitution property. All right, what's your next step? Divide both sides by negative 5. Good. What do you think that's called? Division property. And then let's just write what this is equivalent to. What is 90 minus divided by negative 5 equivalent to? What's negative 5 divided by negative 5? 1, obviously. So by the substitution property, x equals negative 18, I have proven my conjecture. See how this works? You might be thinking to yourself, this is silly. I can do this algebra much faster than writing out all these very particular steps. That may be the case. But if you're ever going to compete for the Millennial Prize, you need a very definitive proof. If you ever succeed in organic chemistry, you need to be able to write very systematic proofs, yes? It's a skill that's used in many disciplines, but math for sure. So we're practicing those skills. I know what your brain did. Let's look at the same problem. I'll tell you what your brain did. It did something like this. It said the given is negative 5 times x plus 4 equals 70. So I'll use the distributive property. I'll get this. Then I'll add 20 to both sides. So addition property, I get this. Divide both sides by negative 5, so I get this by the division property, right? So you get the general idea, but really what we want to write is all of these idealized steps. That's what we're going to practice, is rigor. If you submit a proof to your professor, and you're trying to prove something, even if you're right, if you skip too many steps, then someone's going to have to come behind you and fill in the gaps. And that's happened many times in mathematical history. We want to make rigorous proofs. Great. Take a breather if you need it. Come back and read this with me. Once a statement or conjecture has been proved, it's called a theorem. And it can be used as a reason to justify statements in other proofs. One example is the Pythagorean theorem. It is not self-evident, but once it has been proven from first principles by deductive logic, it is used as a theorem or a true statement in proving other statements. So what's a theorem, and how is it different from an axiom? Do you know? An axiom is a self-evident statement. A postulate is a self-evident statement. It's a first principle. It's a first evidence. Axiom is a self-evident statement. A theorem is not self-evident. You had to use deductive logic from an axiom to get down to a theorem, like the Pythagorean theorem. But once it's been established by deductive logic, it's true, and everybody accepts it as true from there on. That's what a theorem is. It's like a derived truth that everybody's going to use. Okay. Well, we did algebraic proofs, so why not geometric proofs? A geometric proof uses undefined terms, definitions, postulates, and theorems to prove geometric conjectures. Here we go. Given that Q is the midpoint of the line segment PR, write a geometric flow proof to show that line segment PQ is congruent to line segment QR. All right, what's our given? Q is the midpoint of PR. What is our thing we're trying to prove? Prove that line segment PQ is congruent to line segment QR. Remember, that's that ancient geometric thinking of congruence. What's our first step in any proof? I don't care if it's algebraic, geometric, or whatever. The given. What's the given? Q is the midpoint of line segment PR. All right, what's going to be our next step? It's not algebra, it's definitely geometry. What do you think you're going to say? You're going to say PQ equals QR. And you'd agree with that, right? This measure of PQ equals the measure of PR? Of course. How did we get there? What step did we take? We used the definition of a midpoint. That was literally the definition of a midpoint in your textbook. Right? Divides a segment into two equal measures, or into two segments of equal measure. There we go. Now, last step, straight to the conclusion. Line segment PQ is congruent to line segment QR. How do we get there? The definition of congruence, right? Congruence is two segments have equal measure. That's the idea of congruence. Congruence being an ancient geometric idea, and measure being a modern idea. Got it? All right, let's try one more. Maybe try it on your own. Maybe try it with me. Your choice. Given that P is the midpoint of line segment JK, write a geometric flow proof to show that X equals 2. All right. Given P is the midpoint of line segment JK, prove that X equals 2. What's our first little bit here? The given. What is the given? P is the midpoint of line segment JK. Now, what's our next step? Just like before. Yeah, based on the definition of midpoint, we can say that JP equals PK. No problem. What's our next move? Well, JP has a measure of X, and PK has a measure of 5X minus 8. So maybe we just put those in their place, right? JP is X, PK is 5X minus 8. What do you think that property is? That's the substitution property. Substituting one thing for another, that's the same. All right, what are we going to do to both sides to solve for X? Subtract 5X, great. So that's the subtraction property. Then combining like terms, that will form the substitution property. And then we divide both sides by -4, that's division property. Finally, substitution property tells us that X equals 2. All right, folks, you might need another breather here, but let's jump back into it after you take a break. Another way to prove a conjecture is to write a paragraph that explains why the conjecture for a given situation is true. This is called a paragraph proof. Paragraph proofs are also called informal proofs, although the term informal is not meant to imply that this form of proof is any less valid than any other type of proof. Similar to a flow proof, a paragraph proof includes the theorems, definitions, postulates that support each statement. All right, folks, you know in this class, you have to speak multiple languages. You have to speak algebra. We're going to do algebraic proofs. You have to speak geometry. We're doing geometric proofs. Verbal, right? That's where you do paragraph proofs. Okay, we're not doing any numerical proofs today. That's good. But there's another language you learn, fifth language, right? The language of constructions. We could have construction proofs. In fact, much of Euclid's textbook are proofs using constructions. All right, in this chapter, algebraic proofs, geometric proofs, paragraph proofs. Great. How do you write a paragraph proof? Write given and write what you're going to prove. Draw a diagram and label any given information, especially for geometric paragraph proofs. A diagram would be great. Then write the proof. Create deductive argument from forming a logical chain of statements. Justify each statement with a reason that includes definitions, postulates, algebraic properties, postulates, or theorems, and state what you have proved. Let's try this one. Given that C is between A and B, and that line segment AC is congruent to line segment CB, write a paragraph proof to show that C is the midpoint of line segment AB. So what's our given? C is between A and B, and line segment AC is congruent to line segment CB. What are we trying to prove? We're trying to prove that C is the midpoint of line segment AB. How are we going to do this? Well, first thing you're supposed to do is step 2 is make a diagram. So what would your diagram look like here? That looks good. C is clearly between A and B. C is between A and B. And line segment AC is congruent to line segment CB. You can see that. All right. Third step, actually write the proof. You're just going to write it out in words. That's it. Here we go. Proof. If C is between points A and B, then by definition of betweenness, A, B, and C are collinear, and AC plus CB equals AB. That was our literal definition of betweenness. All right. If line segment AC is congruent to CB, then by the definition of congruence, the segments have the same measure, which is that AC equals CB. From the definition of midpoint of a segment, if C is the midpoint of AB, then AC equals CB, and C is the midpoint of line segment AB. Sorry, if C is between points A and B, and AC equals CB, then C is the midpoint of AB. That seems more reasonable. All right, there's logic here, there's steps here. It's not written in a flow proof, it's written in verbal language, but it's conveying the same exact information in a different language. All right, you're going to want to be able to answer these questions. Let's see if you can do it. If not, look up the answers in your textbook or in the class notes, or review this video. What's a postulate or an axiom? What's a proof? What's a flow proof? What's an algebraic proof? What's a geometric proof? What's a paragraph proof? Well, we know what a postulate is, don't we? Or an axiom? It's a self-evident truth in math. What's a proof? This is where you start with first proof principles and you deduce some theorems, or you start with theorems and deduce other theorems. What's a flow proof? This is where you write each of your steps in boxes, and underneath explain what your step is, where you start always with the given and you end always with the conclusion. An algebraic proof. It's a proof where we use algebra. A geometric proof, a proof where we use geometry, right? And as we saw, even in the geometric proof, algebra creeps in, because very often in this class, you move from geometry to algebra and solve. Okay, what's a paragraph proof? That's just a verbal proof, which is going to involve algebra and geometry. All right, folks, here's your homework notes. There are different problem sets for standard and honors. Standard does not include paragraph proofs. Honors does. All right, folks. Thank you.